Welcome to the second week of the program. Hope all of you had a good time, good weekend. And in this week, among other talks, we are going to have two thematic series lecture. One is by Professor Giacomo Gigante from University of Bergamo, and another is by Professor Michael Lacey from Georgia Tech. And it's a pleasure to have you. And he's going to speak on quadrature rules on manifold. The first talk is partitions.
Thank you very much. It is a pleasure to be here. Let me thank the organizers for everything they have been doing during all the week. I've been really treated like, like if I was at home, taking care of, they are taking care of me. Everywhere I go, there's somebody that makes sure I don't get lost. So thank you very, very much to everybody, not just the organizing committee, but to the, thanks a lot. So I will speak about quadrature rules on manifold. This is basically numerical approximation of integrals. So I assume people are not very familiar with the subject. I will make a few examples. Can you hear me? Should I do it? Okay, he'll do it. And so I will make a few examples, and then I will talk about what people use in practical examples, although I'm not an expert on that side, but I think it's fair to say a few things about that. And then I will go to the first part, to the real subject of the talks, which is quadrature rules on manifolds. Okay. So let us begin with this example. So the idea is to estimate the error in numerical integration. So you have your function, you want to compute the integral between 0 and 1, and you approximate that with some Riemann sums. In this example, so you evaluate the function at some points, xj, and then you multiply it by a weight. In this case, all weights are equal 1/n. So in this first example, you take just any point. You divide the interval 0, 1 into n equal intervals. You take any point xj in each interval, 1 in every interval. And then if f is Holder continuous of degree alpha between 0 and 1, then of course you can say that this difference, you can control that with the sum of the integrals on each interval. You take absolute value inside, and then of course the distance between x and xj is going to be smaller than 1/n. So you multiply the supremum of this quantity by the length of the interval, which is 1/n. You have an interval, so 1/n and n cancel out, and you're left with this. And so this is going to be smaller than or equal, since the function is Holder continuous, and the distance between x and y is less than n to the 1/n, then you have 1/n to the alpha, and this number here is the smallest constant that for which the Holder inequality is true. So in this example, what you should remember about this is that what we want to do is find points. I said that you can take any point, but any choice that you make will work well for any function which is Holder continuous. So this inequality will hold with the same 1/n to the alpha for all functions. So you want to find rules that work well for every function. And in some space, okay, now this is a semi-norm, but this is just an example. And of course, you want to have this 1/n to the alpha as small as possible, because of course, as n increases, you want to have a better approximation and you want to have it as soon as possible. So for as few points as you can. The second example, Now, in general, you can also allow different ways. So instead of 1 over n, you can take just omega I, which is some weight. And if you take the error for, well, this is Lagrange interpolatory quadrature rules, it doesn't really matter how you get this. If you don't know, it's okay. So the thing is that for some function, which is say n times differentiable, you have this inequality. So basically, if your function is C infinity, then maybe you can think that these derivatives are bounded, then you have a very, very fast convergence. But the problem is that if your function is in some subable space or whatever, it has some finite number of bounded derivatives, then as the number of points increases, at some point you're going to have to stop, because n is here too, and you might not have n derivatives as you wish. So you cannot use this for our purposes. But what you can do, as I said here, if you want to have a priori estimates, so for every f in some space, maybe C alpha. So the idea is that you fix alpha equal to n, and then you apply this rule to each interval. I mean, you divide this interval AB into, say, m subintervals, and then you apply this rule to each interval. So this difference here, so you have your AB, you divide it in subintervals AJ plus 1, you take m of them, and then you apply your rule to each one of the intervals that you have divided AB into. And so the length of each of these interval is going to be B minus A over M. Then you take the power n to n plus 1, which is alpha plus 1. And then you have 1 over alpha factorial, and then you have the maximum. So now what you really care now is M. You are free to choose M as big as you want. And so you have a decay, which is, well, this alpha is just, I mean, alpha is fixed for us, so we don't care. You just put a constant C alpha. But this alpha times M is the number of nodes that you have taken, because you have alpha intervals, and in each interval you have you have M intervals, and you have alpha points in each interval. So you have a decay, which is the number of points to the minus alpha, and now alpha can be as big as you want. And here you have the maximum of the derivative, of the alpha derivative of your function. So this is something of the type of things that you were looking for. And notice also that your points are somewhat well distributed, because you have alpha points in each interval. So they are not concentrated somewhere, they are more or less well distributed. So this is a second example. Okay, and one of the most used results in numerical integration, especially in higher dimensions, but I will start with one dimension, is this Cox mass inequality. So again, your problem is to approximate this integral with Riemann sums. And the inequality says that you can control this error by means of the product of two quantities. One quantity, this is this star, this is called discrepancy, and somehow it contains the information on how well distributed your points are. And the second term says how regular the function is, more or less. So let's see the precise definition, this star of xj. So what you do is you compare the length of the interval 0t, which is of course t, and you compare that with the number of points xj that fall inside the interval 0t, and you divide that by n. So this quantity basically is the ratio of points that fall in the interval 0t. And you are comparing that with the length of the interval. Okay, so somehow this says how if your points are recover the Lebesgue measure more or less of the interval. And this quantity tells you how badly you do that job, okay? And if you think about that, since t is the length of the interval, you can write it like this. So in some sense, this discrepancy is exactly the same thing as here. So it's the error in the integration, but only for functions that are characteristic functions. So in some sense, you want to control the error in integration. And so you're saying, well, I only have to control the error in a smaller set of functions. And then I have this inequality and I use it. The second part is just the total variation of the function. So you take the interval 0, 1, you take k points, and then you evaluate the difference between two consecutive points, take absolute values and take the supremum. Okay, so next slide. As I said, this quantity is called discrepancy, and as I said, measures the error with respect to functions of this type. This is already something I said. And the discrepancy measures how points are well distributed. And of course, in view of this inequality, it is natural to ask if you are able to find points which have low discrepancy, because as I said before, this is somewhat fixed given the function, and you want this to be small. So what you want is to have points that give you small discrepancy. For example, if you take equally spaced points, then your discrepancy is going to be just the length of the interval in which you divide the length of each of the intervals that you obtain by taking this equally spaced points. And this is actually, at least apart from a constant, this is the best you can do, because if you put n points in an interval, then you're going to have at least a couple of points, which consecutive points, which have distance bigger than or equal to 1 over n. And so if you have an interval here, which maybe you are lucky and you have an interval that gives you 0 discrepancy because the number of points that you have in this part is exactly equal to the length of this interval, then either this interval or this interval will contain the same number of points, but we have a length which is at least 1 over 2 to the n from the other. So you miss the 0 discrepancy by at least 1 over 2 to the n. So this apart from the constant, this is the best you can do, at least as rate of decay. Okay, so this is the best we can do. And so in one dimension, the problems seem to be all right, and somehow just take the equally spaced point. But the situation is might be more delicate than that, because it might be interesting to find infinite sequences for which this happens. And that's because if you take an infinite sequence, maybe you take the first n points of this sequence, and if you want n plus 1 points, you only have to add 1 point, and you already have the evaluation of the first n points. So what happens is that, unfortunately, if you have infinitely many points, you cannot have a discrepancy which goes as c to the n. And there is this remarkable theorem of Schmidt, 73, that says that this discrepancy cannot be smaller than log n over n. If you think about it, I don't know if they see me, maybe. So assume you already have n points here, and you want to add an extra point, and if you go left to right, then you add 1 here, and 1 here, 1 here, 1 here, and then at some point you will have twice as many points on the left side as you have in the right side, but the intervals have the same length, so you're not going to have discrepancy I mean, this is not going to work as a solution. This is not going to be 1 over n. It's going to be a constant. Okay. So you have to find some better solution. And the idea is this van der Corput sequence. So you have to you start with a point in the middle, and then you go 1/4, and then you go here, and then 1/8, and then you want to make sure that you don't forget the second part of the interval. So you add 1/2, and I guess you go here, and then you go back here, and then you get here. So you have to fill your interval in a sort of balanced way, and this is the idea. And in this case, this sequence satisfies this kind of inequality log n over n. Okay. Now I'm going to give a quick proof of Cox-Mass inequality. And in fact, I'm not proving Cox-Mass inequality because I won't be using it. And what I want to prove is something similar that will be closer to what I will do later. So this is the inequality that I'm going to show. So this is the error. And I want to control that with the L1 norm of the first derivative. If your function is absolutely continuous, this is just the total variation as we had in Cox-Mass inequality. And the second term, rather than being the discrepancy, is going to be a slightly different quantity. G is the sawtooth function. Okay. I think x minus half. Okay, this is 1/2. Okay. And somehow this quantity contains all the information on the points xj. And if you think about it a second, this sawtooth function is just an average of the characteristic functions of intervals. So it's something similar to what we had before, the discrepancy. So let's quickly see how this works. This is the quantity we want to estimate. Just write the Fourier series of your function. Fxj is going to be the series as k varies of e to the 2 pi I k xj f hat of k. And you are removing k equal to 0 because this, of course, is f hat of 0. And then you have your sum in j, which just take inside. Now I switch things a little bit. Actually, what I'm doing here, and this is a trick that I will use several times, I multiply and divide by 2 pi I k, because this way here I get the Fourier coefficient of f prime, which is what I want. And this quantity here somehow will become what I want, because the sawtooth function has this Fourier expansion. And then this is the quantity I had before. And of course, this term 1 over 2 pi I k is the Fourier coefficient. And this term here is a modulation that corresponds to this translation in the x variable. And so now I have this identity. And of course, this is just the scalar product of these two functions. And now here I can use Holder's inequality, but I could also use Schwarz inequality, Cauchy-Schwarz inequality, or Holder's inequality with any p and q coefficients. So what I did before was just the L1 norm of f prime and the L infinity norm of this, but I could also use other p's and q's. So the what did I want to say? Okay, I forgot. Doesn't matter. So this is the proof, basically. Yeah. Okay. What I wanted to say is that the proof of the actual Cosma inequality is not difficult and gives you exactly what we had at the beginning, but I just wanted to give you this proof because it's closer to what I'm doing. Okay, what happens when you go to higher dimensions? Because what people really want to do is compute integrals in very, very high dimensions. So this is a delicate problem. You have to start with a definition of Vitali variation, which is one of the first attempts at defining functions with bounded variation in higher dimensions. So you take a function and a subinterval of 0, 1 to the power d, and delta jf is an alternating sum of the values of f at the vertices of j. So you have your function in the unit cube, you take your interval j, and I guess you take your function and this delta is just the evaluation of the function at these 4 corners with signs which alternate. And then what you do is you take a partition of your unit cube and you repeat the same thing for each j, sorry. Oops. For every j, and you add up and then take the supremum as the partition values. This is the Vitali variation, but that's not enough. We need to repeat the Vitali variation in each dimension for each side of our cube, and you add up and you add everything. So this is going to be, I'm going to call that the calligraphic of f. Okay. So this variation works well for smooth function, but cannot be applied to most functions with simple discontinuities. For example, if you take this triangle and you take this partition, just divide into squares. If you see these squares which intersect this side, have 3 points inside, which means you're going to add 1 here, minus 1 here, that gives you 1. Yes?
Please go back to the previous slide.
Sure.
So in 1D, does this reduce to the usual variation?
I think so, yeah. Okay. Yes, because you're going to have minus plus, and you add f in this. Take absolute, no, it's not telescopic because you have absolute values. Now the variation you cannot, you have to.
So in 1D, that's just a difference of the.
Yes. So you're taking differences with alternating,
okay.
right?
Now you have to choose these.
Yeah. But as I said, the bad part is that, of course, here you're going to have a 1, a 1, a 1, another 1 here. And of course, if I take finer and finer cubes, in this variation will go to infinity. So this doesn't have bounded variation, and I mean, this is why this variation is not really used in other situations. Yes?
I don't get 3K, the definition of 3K.
K is just some way to say that you are doing this in every dimension. So just think, you repeat, K would be 2 here and 1 in each of these. This is just a bad notation to say that you are repeating the Vitali variation in every K-dimensional face of your cube. So the D-dimensional face will be the cube. The D-1 dimensional face will be just the faces of your cubes. Then you repeat that for the, how do you call that? The one-dimensional faces, which are just the, okay. This is just a bad notation because otherwise it would be a terrible notation, very, very long, and this is just, okay. Yeah, that's a finite sum. That's definitely a finite sum, so it's not a problem because you're, sorry. Okay.
From 1 to d minus 1.
Yeah, to 1 to d to d. And
D is the full.
this is the full dimension, yeah.
But you do not do the partitions, you just do in the corners.
No. You do. I mean, you do the partition here, and then you do the partition here, and you take the Vitali variation of the restriction of your function to this side. Okay.
So you have a partition, and then on each face of the.
I mean, you take the partitions to you take the supremum in each side, and then you add. So you take the for example, here you take the variation, the total variation of your function here, and then you do it here, then here, and then you do it in the full dimensional case.
So I'm just confused. Is it just the 0, 1, d-dimensional? The faces are just on the outside. They're not.
No, the face, yeah. So you first do it in each of the faces of your full space, which is just the unit cube. And so how do you do it? You divide that into, and then do the supremum of the variation here, and then you repeat that for every part, and then you do it for this face, and then you do it for the whole cube. And every time you do the supremum, and then you.
So my question is that the lower dimension is only on the outside face.
Yes. Yes, only on the outside, yeah. Okay. And then you have the definition of discrepancy in this case too. And well, this is again the difference of between the length of the interval, which is now just a box. So the volume of the box in this case, and the ratio of points that fall within the box among the full number of points. And so basically the Cox-Malafka inequality says that this integral is bounded by this variation, this Hardy-Krauss variation that I mentioned before, times the discrepancy in this sense. So what is bad about, I mean, well, before that, if you take equally spaced points, so you take a grid of points, this is not going to work very well. It doesn't have low discrepancy. So the idea is you take these points in a grid. And why it doesn't have small discrepancy? That's because basically this rectangle contains the same number of points as this rectangle, and their discrepancy, if one of them has 0 discrepancy, the other will have a discrepancy which is going to be how do they call the number of points in each dimension? Okay, so this is 1 over k, which is going to be, actually is equal 1 over square root of n in 2 dimensions. Okay, so in d dimensions, you're going to have a discrepancy which goes as n to the minus 1 over d, okay, which is too big, because you can choose points which have discrepancy bounded by this quantity. For example, in 2 dimensions, what you can do is take essentially the graph of the van der Corput sequence that we saw before. And maybe I have a picture here. So you see, when you are here, you take 1/2, then 1/4, 1/4 plus 1/2, 1/8, 1/8 plus 1/2, etc. And you see these points are well distributed, and they are fewer than the points in a grid, basically. Okay, so and you have this this discrepancy. And there is this remarkable theorem of Roth that says that you cannot do better than log n to the d minus 1 over 2 over n. The constant that depends only on the dimension. The conjecture being that you cannot go below this quantity. And Schmidt proved in 73 that this is true for d equal 2. And in higher dimensions, the only result that I believe, the only one that I know at least, and I believe this is the best thing you can do, Billy Clacy and Vagar Shakyan prove that you can add a positive constant to this exponent. So we're still far from this power. Okay. Second problem with say this kind of solution, the grid, is that the number of function evaluations increases with the dimension very quickly. For example, if you have 200 dimensions and just take k equal to 2, so you only evaluate your function at the corners of your square or whatever, then you're going to have 2 to the 200 evaluations. This is more than 10 to the 60 evaluations. You very quickly go to the point that, you know, as mathematicians, we really don't care. I mean, big number is just a big number, but if you really have to compute things, you're gonna. Okay, so one alternative which is used very often is this Monte Carlo method. It doesn't really give you a bound, it more properly gives you an estimate, because what you have is that if you take an L2 average, as your points xj vary freely in your box, then you have this control, 1 over square root of n times the variance of the function. And the interesting thing on this estimate is that this doesn't depend on the dimension. So this is why this is used very often. What they do is just take random points xj and repeat that a few times, and then they take the average of what they get, and they are fine with that. So it works in high dimensions. The problem is that it's really hard to produce real random points. So they use pseudo random points. And so I have a proof here, but I think I skipped that. So back to what I'm really willing to do today and tomorrow and on Wednesday. So let us start with the setup. We have a smooth, compact, d-dimensional Riemannian manifold without boundary, and I will call d mu the normalized Riemannian measure. So the measure of our manifold will be 1. I will call delta the positive Laplace-Beltrami operator. So this is usually called minus delta, but just to use the notation. This is self-adjoint in L2. It has a sequence of eigenvalues. The first one will be 0, and then L1 square, L2 square, etc. And an associated complete system of eigenfunctions that I will call phi k. These are in increasing order, and I'm taking them with repetitions. So this means that the k essentially corresponds to the eigenfunction. Okay. For example, if you are on the d-dimensional torus, the Laplacian will just be the usual Laplacian, and these are the eigenvalues, and the eigenfunctions are the exponentials. So if you are not so familiar with manifolds, just think of this, or you can think of the d-dimensional sphere in Rd plus 1. These are the eigenvalues. Of course, these are listed without repetitions, but for each one of these eigenvalues, the eigenfunctions will be the restriction to the sphere of homogeneous harmonics, polynomials of degree. These are the spherical harmonics. So these are the two examples that one might keep in mind. And of course, I will call f hat k the Fourier coefficient corresponding to this orthogonal system. Okay, now I want to define Sobolev spaces. I will give 3 equivalent definitions. alpha will be the degree of the number of derivatives. And this is W alpha P will be my Sobolev space. First definition is just you require that the identity plus the Laplacian to the power alpha 2 of F, alpha half of F is in LP. So I just write this, say alpha derivative more or less of F and take the LP norm. This is the first definition. This has to be finite. The second definition is by means of potential spaces. So you define your Bessel kernel, which is this, you sum in K from 0 to infinity. And when a function F belongs to this space, if and only if it is the Bessel potential of a function G in LP, which means that if you integrate your function G against this kernel B alpha xy, you get F, and the alpha P norm of F will just be the P norm of G. And the third definition, well, you can do it by localization. So if you take a smooth function H, which is compactly supported in a local chart, then what you want is that the, say, pullback of H times F will be in alpha, W alpha P of RD. So these are all equivalent definitions for your Sobolev spaces. I will mostly use this by Bessel potential. Okay. Notice that by Sobolev embedding, if alpha is greater than D over P and F is in W alpha P, then F is Holder continuous of degree alpha minus dP. Okay. So now what I want to do is you fix your points, you fix your weights, and you want to give a priori estimates for the error in numerical integration. And of course, you want that to be true for all functions in some Sobolev space. So a natural requirement is that alpha is bigger than D over P, because this way we obtain continuity, and so it makes sense to define f of xj. So this is a minimal requirement, let's say. So again, as a motivation, you assume that there exists a decomposition of your manifold into this joint union of U1, U2, Un, and each piece has measure 1 over n, for example, and the diameter is what you expect, at most n to the minus 1 over d. So something like this. This has measure 1 over n, and of course the diameter will be smaller than 1 over n to the 1/2 in the two-dimensional case. Okay, so the natural, assume you can do that. And if you take, as we did at the beginning, in the very first slide, you take one point xj in each uj, and then the estimate, well, you bound this integral with the sum of the integrals on each of the sets uj, and then you take the supremum of this difference in each of the regions. You have n regions, so n times 1 over n cancel out, and you're left with this. And because your regions have diameter which is controlled by n to the minus 1 over d, and you can use the fact that your function is in your Sobolev space, so it is Holder continuous with this degree, and so you obtain this order of decay. Okay. So the thing is, we want to show that you can improve this exponent from minus alpha over d minus 1 over p to minus alpha over d. And we also want to show that this is best possible. Okay, so we already got close to the best possible here. For example, if p is infinity, then we are already there. So the first theorem is this result. This is a lower bound for any p, And if alpha is bigger than d over p, you have a constant such that whatever set of points you take and whatever weights you associate to that choice, you always find a function f with alpha derivatives in LP, for which this error is going to be greater than or equal to this bound. So you cannot do better than this. There are previous results on the two-dimensional sphere and p equal to 2, and later on compact two-point homogeneous spaces for p equal to infinity. The proof is actually, I can give you a quick idea. You take epsilon so small that for all integers, and you can find 2n disjoint balls with the diameter that you're looking for. Since you have n points and you have 2n balls, there are at least n balls with no points xj inside. Now you take a bump function Cj supported on each of the n empty balls, and you can do it with in such a way that your function has integral 1 over n. You just take your bump function that has integral 1 and then dilate it by 1 over n to the minus 1 over d. Okay, so the integral will be 1 over n. And accordingly, the Sobolev norm will be controlled by this quantity. You just do your computations with the derivatives. And at least when alpha is integer, this is very, this is immediate. And so now you take the function is the sum of this Cj, and this is all additive, at least let's say when k is integer. So the alpha p norm will be just basically the sum of these quantities. So you have n to the alpha over d, and the integral will be 1 because you have n of these. And so this error, since your function f is supported away from the points xj, because your functions cj were located where there were no points in the balls which had no points, this quantity is 0, this integral is 1, and we just said that f alpha p is smaller than this quantity. So you see, you get exactly the type of estimate that we wanted. This error cannot be bigger than this quantity, okay? So this is a first lower bound. And okay, I think I'll skip this and I'll just go to the result, and because I'm short in time. So this is the upper bound that we obtain. If you take an alpha between d over 2 and d over 2 plus 1, and again you do this job of partitioning your manifold in the disjoint union of sets of measure omega j, then you have a constant independent of n such that, okay, let's see what is happening. This is a probabilistic result. So you take your error and you take the supremum as alpha. Let's say this is basically the norm of the functional that takes f to the error. Okay, so this is just the norm of a functional, and then you take averages as xj varies in each of the sets uj. So you take x1 in u1, x2 in u2, and then you integrate. So you're taking averages, okay? And you obtain this estimate. You have a constant times the maximum of the diameter to the power alpha. So in particular, if you can obtain a partition of your manifold with sets which have this bound on the diameter, then this immediately becomes c to the times n to the minus alpha over d. So the norm, so basically you can find points xj within uj such that the error has a norm which is controlled by this quantity, which is exactly what you were looking for. Okay, so the problem here is that this is true only for alpha smaller than d over 2 plus 1. So if alpha is bigger than this quantity, then you cannot really go beyond that. So in fact, there were previous results in the case of weights equal to 1 over n. Okay. I'm going to skip the proof of this result. There is a general result which we proved later, and basically this is the LP norm result. And so for any p bigger than 1, take q to be the conjugate index of p. If alpha is between d over p, remember this is for continuity purposes, and alpha is also less than d, you can split the M as the disjoint union of regions, each one of measure approximately 1 over n, and diameter approximately n to the minus 1 over d. And you do the same job only with a Q norm, then you get the best possible order of decay when alpha is smaller than d over 2 plus 1. And as soon as alpha gets larger than this quantity, you don't get better decay only because alpha gets bigger, okay? And notice that this is an upper bound, but also a lower bound. So you cannot really improve this exponent minus 1/2 minus 1 over d, okay? The proof is essentially the same as in the two-dimensional case, only you need to use this Marcinkiewicz-Zygmunt inequality, which is an extension of Khinchin's inequality. And this is a bit technical, I can skip that. So I will stop here. Let me just recap what we have shown. We have shown that if you take any choice of nodes and weights, the norm of your functional will be bigger than or equal to than this quantity. With probability close to 1, any choice of points, each one in a region, will give you this control on the norm, but only when alpha is between these two quantities. The question is, can we take nodes that give us a decay which is the best possible also for greater values of alpha? This is the first question. And the second question is, assume that you fix omega j, for example, take omega j to be 1 over n for all j, just the classical case. Can you build partitions with these properties? So omega j is exactly equal to 1, sorry, the measure of 1 over j is exactly equal to 1 over n, and the diameter is controlled by n to the minus 1 over d. Can we do that? So these are the two questions that I will try to answer in my next two talks. Okay, so that's it for today.
Any questions or comments?
So anything happens at the endpoint?
Yeah, at the endpoint, at the moment, okay. At the endpoint, we have this logarithmic loss, and then when alpha gets a little bigger than the critical index, we can remove the logarithm.
What happens with the other endpoint, the endpoint of the Sourabh embedding theorem?
Okay, but you might not have continuity, so
anything symptomatic. You have other kind of embedding theorems. Here you are using the Mohali embedding theorem.
okay.
In that case,
We never went through it. I mean, maybe you can do something with an average. Yeah.
Here you are taking average.
Yes, that's right. Yes, but yes, in fact, we could have done something like that. But I mean, in principle, because we always have in mind that people eventually want to use this thing, so you really have to evaluate the function. But okay, sure.
What about this condition? That means the disjoint union of uses.
Yeah.
Is it you always want the volume to be small, and is large?
You want the volume to be, say, 1 over n. What you want is the diameter to be small. You don't want to. So what you want is something like this. What you don't want is partition with pieces that are long. You don't want this. Okay. So basically, you want that each of the pieces you split that you're taking has the smallest possible diameter. And the smallest diameter you can take is n to the minus 1 over d, because of course you're in a manifold and the volume of the balls is going to be controlled by the diameter to the power d. Okay. And so this is, if you have smaller diameter than that, your volume is going to be smaller than 1 over n, so it's not conceivable. Okay.
It's always possible to do that.
Yeah, I will answer that on my probably tomorrow or on Wednesday, depending on time. For example, on the sphere, it is well known that you can do it. Let me give you okay, so there are several ways to do it. One nice way to do it on the sphere is by with convex sets and let me give you an idea. You can find this in Bondarenko, Radchenko, and Vyazovska's paper on these matters. Say you take your two-dimensional sphere and start dividing it in the, say, spherical cube. So I have 6 faces. Oh, you know what I mean. So you have a cube within your sphere. You're taking the points and joining each point with a great circle. And what you can do is I give you a little n, and then you take big circles starting from the North Pole, and you divide this into n pieces, all with the same area. If you move them each great circle, you can definitely do it, and you repeat that in the other direction. And since these are great circles, these are going to be all convex, and you're going to have 6 times n square pieces, all with the same area, which is going to be 1 over this number, and of course, small diameter. Okay. So this is a way to do it on the sphere. This is this is not a generic number, but you can adapt this technique to get any number. I'm sorry?
How do you control the width?
Well, basically, because you are in a face of a spherical cube, so this is basically Euclidean. So this is like a box. Okay.
Any more questions? So if not, let's thank the speaker for a nicely placed.